This video covers Excel functions that measure central tendency in a data distribution. Measures of central tendency let us know a central value around which all other values are distributed. There are several Excel functions that help us to estimate a central value. Cell range A1 to A21 has the data. The first step is to count data points in the data distribution. We can use count function to count data points. In cell H3, let me enter equal to, count, open parentheses, and function. You will see count function dialog box. Enter cell range A2 to A21 for value 1 and click OK. You can see that the count function has returned 20. This means the data distribution has 20 values. Next, let me compute arithmetic mean. Arithmetic mean is one of the measures of the central tendency. Position or frequency of values does not determine arithmetic mean. Instead, the magnitude of values in the data distribution determines the arithmetic mean. We can use average function to compute arithmetic mean. In cell H4, enter equal to, average, open parentheses, function. You will see average function dialog box. Enter range A2 to A21 in argument number 1 and click OK. You can see that the average function has returned 19.6. This means, in most cases, the distribution values are clustered around 19.6. Now let me move on to the median. The median is the most middle value in a sorted data array. Magnitude or frequency of values does not determine the median. Instead, the position of values in the data distribution determines the median value. In this sense, median measures central tendency differently than the mean. In cell H5, let me enter equal to, median, open parentheses, function. You can see median function dialog box. Enter range A2 to A21 in argument number 1 and click OK. You can see the median function has returned 19.5. This means the value 19.5 is the midpoint of the sorted data array. In most cases, the values in the distribution are clustered around the midpoint. Next, measure of central tendency is mode. Mode is the most frequently occurring value in the data distribution. Magnitude or position of values in the data distribution does not determine the mode. Instead, frequency of their occurrence determines mode. A distribution can have one or more modes. Excel has separate functions for computing single and multiple mode in a data distribution. Let me begin with computing single mode. For this, we must use Excel function mode.single. In cell H7, let me enter equal to mode.single, open parentheses, function. You will see mode.single dialog box. Enter cell range A2 to A21 in argument number 1 and click OK. The function has returned the value 5. This means the value 5 is the most occurring value in the data distribution. In most cases, one can expect the values of mean and median to be closer to the mode. If no mode is present, then the function will return NA error. Let's see this with an example. We have another data set in cell range J2 to J6. The frequency of all values is 1, and hence there is no mode. In cell H8, let me enter equal to mode.single, open parentheses, function. Enter cell range J2 to J6 in the argument number 1 and click OK. You can see the function returns error NA. Now let us look at multiple mode. For this, we must use Excel function mode.multiple. In cell H10, let me enter equal to mode.multiple, open parentheses, function. You will see mode.multiple dialog box. Enter cell range A2 to A21 in argument number 1 and click OK. Mode.multiple returns 5, 38, and 26 as mode values. This means that these values have the same highest frequency. Presence of multiple modes diminishes the power of any one mode to be the measure of central tendency. Next, let us focus on the measures of dispersion. Dispersion is the extent to which the values are dispersed around a central value. Measures of dispersion measure the extent of dispersion. This video covers some Excel functions that measure dispersion. Cell range A1 to A21 has the data. The first measure of dispersion is range. Range is the difference between the highest and the lowest values in the distribution. We can use max and min functions to find the range. Let us begin with finding the maximum value. In cell J2, enter equal to max open parentheses function. You can see a max function dialog box. Enter A2 to A21 in the argument number 1 and click OK. You can see that the max function returns 38. This means 38 is the highest value in the distribution. What we want is the difference between the highest and lowest values. Therefore, we must reduce the lowest value from 38. Let me modify the cell formula in cell J2. I will select J2 and click F2 to extend the formula. Let me enter minus, min, open parentheses, click on FX. You will see min function dialog box. Let me enter A2 to A21 in argument number 1 and click OK. You will see the formula returns the range value 37. This means the lowest value is 1, and the difference between the highest and lowest values is 37. Higher the range is higher the extent of dispersion around the central value. The next measure is the mean absolute deviation. It means it measures average of deviations of each value from the arithmetic mean. It is sometimes referred to as average deviation. While the range measures deviation between two extreme values, the average deviation measures the deviation of each value from the central value. In this sense, average deviation is robust than the range in measuring dispersion. Av-dev function returns average deviation. In cell J4, enter equal to av-dev, open parentheses, function. You'll see av-dev function dialog box. Enter A2 to A21 in the argument number 1 and click OK. You can see that the av-dev function returns 11.7. This means, on an average, the deviation of each distribution value from its mean is 11.7. Higher their average deviation, higher is the dispersion. Excel has separate functions for average deviation and standard deviations, because their computation procedure is different. Average deviation is the average of the absolute deviations from the mean, whereas standard deviations is the square root of the average of the squared deviations. Next, let's focus on standard deviation and variance. In Excel, there are two standard deviation functions, standard deviation.p and standard deviation.s. Similarly, there are two variance functions, variance.p and variance.s. The functions ending with .p measure dispersion in the input array values. Here, p is an abbreviated form of population. Therefore, we refer to these measures as population variance and population standard deviation, whereas the functions ending with .s estimate dispersion in a larger set of values from which the input array is drawn as a sample. Here, s is an abbreviated form of sample. Therefore, we refer to these measures as sample variance and sample standard deviation. In this video, we're going to cover functions ending with .p. Those functions ending with .s will be dealt in some other context. Let me begin with measuring population variance. In cell J6, enter equal to variance.p, open parentheses, and click on function. You can see variance.p dialog box. Enter cell range A2 to A21 in argument number 1 and click OK. You can see that the function variance.p has returned 173.14. 173.14 is the sum of the squared deviations from the mean divided by the number of observations. Now let's compute the population standard deviation. In cell J7, enter equal to standard deviation.p, open parentheses, and function. You can see standard deviation.p dialog box. Enter cell range A2 to A21 in the argument number 1 and click OK. You can see that the function standard deviation.p has returned 13.15827. 13.15827 is the square root of the sum of the squared deviations from the mean divided by the number of observations. The next measure of dispersion is the coefficient of variation. Wherever two distributions have the same mean, one can use population variance and population standard deviation to compare dispersion. In case of different mean values, one should use coefficient of variation to compare dispersion. Coefficient of variation is equal to population standard deviation divided by the average value. Let me show you how to compute coefficient of variation. This computation will be a two-step process. In step 1, let me enter equal to standard deviation.p, open parentheses, in cell J9 and click on function. You will see standard deviation.p dialog box. Enter cell range A2 to A21 in the argument number 1 and click OK. You will see that standard deviation.p function returns 13.15827. In step 2, let me select J12 and click F2 to edit formula. Then extend the formula by entering /average, open parentheses, and then function. Now we will see average function dialog box. Enter cell range A2 to A21 in argument number 1 and click OK. You can see the formula returns coefficient of variation value 0.67134. This means distribution standard deviation is 0.67134 per unit of mean. This per unit measurement is comparable across distributions. This video covers skewness and kurtosis in data distributions. Both measures indicate the shape of the curve obtained by plotting frequencies of the distribution values. Skewness measures asymmetry in curve shape on either side of the center, whereas kurtosis measures the peakness in the curve shape. Let me first cover skewness. In cell J2, let me enter equal to skew, open parentheses, function. You will see the skew function dialog box. Enter cell range A2 to A21 in the argument number 1 and click OK. You will see that the skew function has returned the value 0.069798. Skew function returns value 0 for symmetric distribution. The value 0.069798 is close to 0. This means this distribution could be characterized as mildly positively skewed. More values in the distribution are distributed towards right of the center. On the other hand, negatively skewed distributions will have more values to the left of the center. The next measure is kurtosis. The kurtosis value for a normal peakness curve is 3. The Kurt function in Excel returns deviation from the normal peakness. Negative Kurt values indicate less than normal peakness, while positive Kurt values indicate more than the normal peakness. Therefore, Kurt value is often referred to as excess kurtosis. In cell J4, let me enter equal to Kurt, open parentheses, function. You will see Kurt function dialog box. Enter cell range A2 to A21 in argument number 1 and click OK. You can see Kurt function has returned the value negative 1.51956. This means the distribution height is less than the normal peakness. If we really want to measure the actual peakness of the distribution, then one should increase the value returned by Kurt function by 3. In cell J5, I will enter Kurt function with cell range argument A2 to A21. Now, let me edit the formula and enter +3, and then press enter. You can see the modified function has returned the value 1.480442. This value is less than half of the normal peakness. This means a fair number of values are distributed towards extreme ends, resulting in a flat center.